Welcome to this week's lecture where we're going to cover three related topics that come together when we build a real modern Windows application. That is the Universal Windows Platform, Event-Driven Programming, and XAML, XAML. So here's how they connect. UWP is a platform that lets your app run across every kind of Windows device, whether that's desktop, tablet, Xbox, and more. Event-driven programming is a paradigm that makes your app interactive, responding to clicks, taps, and other user actions. And XAML is the markup language you'll use to actually build the user interface that those events come from. So by the end of this lecture, you'll understand what makes a UWP app distinctive and how events flow from a user's click all the way to your C# code, and how to read and write basic XAML. So let's start with the big picture. The Universal Windows Platform, or UWP, gives you one common app platform that runs across every device powered by Windows. So we have a single UWP codebase that can run on a desktop PC, a tablet, and an Xbox without you needing to write separate versions for each. And so this is a big deal because before UWP, building for multiple Windows device types often meant maintaining multiple, mostly separate code bases. UWP collapses that down to one app, one code base, targeting a shared set of core APIs. So let's touch on four core features shown at the bottom of the slide. UWP is secure. Our app has to declare exactly which device resources and data it wants to access, such as camera or location data, and the user has to explicitly authorize that. Adaptive UI. This is the same interface where it adjusts itself to different screen sizes, resolution, and DPI settings. Store distributed, which means the app is available through the Microsoft Store, which also gives you built-in ways to monetize it. And engaging. UWP apps can use features like live tiles and push notifications to keep users coming back. So the takeaway here is that UWP allows you to build once, declare what you need, and reach users wherever they're running Windows. So let's take a little more of a closer look at each of those four features because each one solves a real practical problem for both developers and users. The idea of being secure by declaration. Rather than an app silently grabbing access to your camera, your contacts, or your location, a UWP app has to explicitly declare upfront which of those it needs, and the user sees and approves that request. This builds trust and reduces the risk of an app behaving maliciously or unexpectedly. A common API on any device means whether you're targeting a desktop PC, an Xbox, a mixed reality headset, or whatever it is, the same core UWP APIs are available, so we can write our logic once against those APIs and it works everywhere those APIs exist. Microsoft Store distribution allows for the installing and uninstalling of a UWP app in a clean environment. There's no machine rot, meaning that leftover registry entries or orphaned files are cluttering up the system over time the way older style Windows installations sometimes do. And being in the store gives you built-in discovery and monetization options. Engaging by design is where we get access to features such as live tiles on the start menu, push notifications, and integration with features like Windows Timeline to let your app stay present and useful to the user even when it's not actively open. And one more detail worth mentioning. UWP apps can be programmed in C#, C++, Visual Basic, or JavaScript, and for the UI specifically, you have choices of using WinUI, XAML, HTML, or DirectX. So in this course, we're focusing on C# with XAML. That is one of the most common combinations, but you do get a lot of options. So if later you want to make this kind of application, but maybe you feel more comfortable in JavaScript or you want to move away from XAML and use WinUI, you have options to do that. So let's talk about adaptive controls and input functionality. One of the most practical and useful things with UWP is how its UI elements adapt automatically. The same button, the same slider, the same layout panel can resize and rescale itself depending on the screen it's running on without you having to run any separate UI code or write things like style sheets for each device. So have a look here on the left at the different input types that UWP apps handle out of the box: keyboard, mouse, pen, and touch, and even things like Xbox controllers. Your app doesn't need special case code for each of these. UWP's common input handling means a button click works whether it came from a mouse, a finger tap, or a controller press. On the right side, the small screen and large screen boxes represent that the same UI can adapt to very different amounts of space. Universal controls and layout panels automatically adjust based on the screen's resolution and DPI density, so a button that looks correctly sized on a small handheld device also looks correctly sized on a large desktop monitor without you having to do any manual recalculating or pixel values. So our real-world example here: a photo app might adapt its layout for one-handed use on a small device, but take advantage of all the extra space when running on a desktop. The controls can adapt automatically, but the user experience design, or how you choose to lay things out for each context, is still something that you, the developer, get to think through deliberately. We also have the common API surface across devices. So let's talk about what this means in practice. In the center, we have the UWP core APIs, radiating out to 4 device types: desktop, tablet, Xbox, and mixed reality. The same core APIs connect all of them. If your app sticks to using only these core APIs, it will run without modification on any of these devices. This is fundamentally different from the pre-UWP world, where targeting an Xbox versus a desktop PC might have meant largely separate development efforts. With UWP's common API surface, you write your app once against a shared set of APIs, and Windows handles making sure those APIs exist and behave consistently across every device type. So we talked about multi-language support. So if you work with C++, a UWP app written in C++ WinRT additionally gets access to the Win32 APIs, which are then implemented by all Windows devices. So that gives C++ developers an extra layer of capability beyond the standard UWP core APIs, while C# developers typically work directly with that core API set. So what is event-driven programming? We're going to shift into our second major topic of the lecture. This is a different way of thinking about how your program runs compared to this simple top-to-bottom, line-by-line execution that you've been working in so far with console. In event-driven programming, the flow of your program is determined by events. Things like a user clicking a button, a sensor producing a reading, or a message arriving from another part of the system. The code sits ready, waiting to respond to whichever event happens next, rather than following one fixed predetermined sequence. So have a look at the flow of boxes here. A publisher, for example, a button control raises an event, like click. That event then notifies the subscriber, which is your event handler code, that something happened, and the handler runs in response. So let's nail down the vocabulary, because you know how important it is for us to sound like we know what we're talking about. These terms come up constantly. The publisher is the class that raises or sends the event. In UI programming, this is almost always some kind of control, like a button. The event handler is the delegate or method that's written specifically to respond when that event fires. The subscriber is the code that registers itself to receive that event in the first place. Subscribing is how your handler gets connected to the publisher's event. So it's kind of elegant. The publisher doesn't need to know anything about who's subscribed or what their handler code actually does. It just raises the event up like a flag and trusts that everyone who's interested will respond. So let's make this a little more concrete with an example of UI development. So we have a button click. This slide shows both halves of the picture, the XAML that defines the button and the C# code that handles the click. So take a look at the XAML at the top. We have a button with its content set to click me, and the click me attribute is set to on button click. Now, if you've worked with things like JavaScript, working into HTML, you're going to see that XAML feels very much like a flavor of that same idea. So this click attribute is doing the subscribing for us. It's telling the framework, when this button's click event fires, call the method named onButtonClick. Do note here, we don't put the parens on the back of onButtonClick, even though it is a method. And if we look at onButtonClick in that code at the bottom, it does have parameters that you would think you need to send as arguments, but they are sent automatically by the system, so we don't put anything in the parens either. Now that's not true if we're writing like a click handler that does take some kind of parameter from the UI, like a user ID or something that you have access to. You would need to pass that, but I just want to point that out in this example because that's a common question. So in our C# code, we can see onButtonClick as a method. It has two parameters: object sender, which tells you which control raised the event, and that's sent automatically, and routed event args e, which carries additional information about the event itself, again sent automatically. Inside the method, you write whatever logic should run in response to the click. So here we just have a quick, output text, hello XAML. And so when the button is clicked, whatever output text is, probably some kind of text box, then that text would show up in the text box. So this is what sums up the key relationship here at the bottom. The click attribute in XAML is the thread that connects the visual button you see on the screen to the actual C# method that runs when someone clicks it. So let's talk about why this paradigm is so dominant in UI development specifically, and why event-driven programming. So the big ideas here are decoupling. Because the publisher of an event doesn't need to know which methods or components are listening, your code stays loosely coupled. You could add, remove, or change event handlers without modifying the button control itself. This separation makes large applications much easier to maintain over time. Responsive UI. This connects directly back to the async and await we talked about last week, which, by combining event handling with asynchronous programming, a UWP application can respond to user interaction immediately, even while a longer operation, like a network call, is happening in the background. Then flexibility and scalability. As your application grows, you can keep adding new event handlers and new behaviors without restructuring everything that already exists. Needing a new button that does something different? Just write a new handler and then subscribe it. The existing event-driven structure of your app accommodates that growth naturally. So what is XAML and why do we use it? XAML, which really stands for Extensible Application Markup Language, is a declarative markup language used to define user interfaces. You'll see it in the Windows Presentation Foundation, also called WPF, in our Universal Windows Platform, UWP, or in the older Xamarin Forms. So the key word here is declarative. Instead of writing C# code that imperatively constructs each UI element step by step, you write XAML markup that simply declares what the UI should look like, and the framework handling turns that declaration into actual visual elements. This is a little bit of marrying the idea of HTML into a more programmable interface. So some big advantages, right? XAML helps keep our UI design separate from our application logic. This means a designer who's skilled in visual layout can work on the XAML, while a developer focuses on the C# code behind, and the two can largely work independently on the same project. Readability and maintainability. Because XAML is hierarchical and structured, much like HTML or really the extensible predecessor, which is XML, elements nested inside of other elements, it's easy to read and understand the structure of a UI at a glance, even in a fairly complex layout. We also get rich tooling support. Visual Studio and the tool Blend for Visual Studio give you things like drag and drop design, property editors, and live preview of your XAML as you build it. This is a pretty substantial productivity boost compared to writing all of your UI purely in code, and then you have to run it to see what it actually looks like. Then we get simplified data binding. XAML makes it straightforward to connect our UI elements directly to a data source or a piece of application logic, often with minimal code, which allows you to load in things like lists or drop-down boxes or populate things very easily. So let's look through an actual piece of XAML line by line so the syntax feels less abstract and we get a better handle on what we're talking about. So at the very top, the window element is the root of this particular UI with a title, a height of 200, and a width of 300, and those are the dimensions of the window when the application runs. Inside that, we have a grid. This is a root layout container for the Windows content. Inside the grid, we have a stack panel with its horizontal alignment and vertical alignment both set to center, meaning whatever is inside of the stack panel will appear centered in the window. Inside of the stack panel, we have two children, a text block given the name output text so we can reference it later from C# with a font size of 20, and a button with its content set to click me, and a click attribute wired to a method called clickMeButton_click. On the right side, we see some quick definitions. Grid is the root layout container for this Windows content. Almost every XAML page starts with some kind of layout container like this. Stack panel arranges its children vertically by default and centers them here because of those alignment properties we've set. X:\name is the attribute that assigns a name to an element specifically so it can be referenced from the C# code behind, and without that name, our code would not have any way to reach that text block to change its text. So let's complete the picture by looking at the C# code file that pairs with this XAML and trace through exactly what happens when the user clicks the button. So main window is declared as a partial class inheriting from window. Inside its constructor, the very first line is initialize component. This is a generated method that reads the XAML we just looked at and actually creates all of those named UI elements like output text as real objects we can then reference in code. Then we can see the clickMeButton_click method. This is our event handler. The exact method name that we wired up in the XAML's click attribute, and inside it a single line calling the output text.text property and equaling it to a string hello XAML. This will directly update the text block's content when the button is clicked. So let's trace through the full sequence of events. Step 1, initialize component runs when the window is constructed. That loads the XAML and creates the named UI elements. Then, when the app is running and the user actually clicks the button defined in the XAML, it will raise the click event, and because of the wiring we set up in the XAML, that invokes our clickMeButton_click method. The handler code runs, sets the output text.text property to the string, and the UI instantly updates to show hello XAML. So this is the complete loop. XAML declares the UI and wires up the event. C# implements what happens in response, and the two come together seamlessly at runtime. And this is essentially the simplest example of event-driven programming. So let's recap what we've learned in this lesson. First, UWP provides one common app platform across every Windows device, desktop, tablet, Xbox, and more, built around a shared set of core APIs. Adaptive controls and layout panels adjust automatically to screen size, DPI, and input type, so the same UI code works across very different devices. Event-driven programming means your program's flow is driven by events, user actions, sensor data, or messages, rather than a single fixed sequence. Publishers raise events, and subscribers' event handlers respond, keeping components decoupled and easy to maintain or extend. XML declaratively defines your UI, cleanly separating design from C# application logic that lives in the code behind. The click attribute in XAML, and attributes like it for other events, connects directly to an event handler method in the code behind, completing the loop from user interaction to running code. So we don't get too deep into XAML and UWP in this course. It's more to get you into the idea of event-driven programming and understand how to connect your UI elements directly to your code behind so that you can set up properties like what you saw today in the output text. I do encourage you to learn a little bit more about this, and if you are thinking about maybe taking on a side project or writing a little application of your own, give the Universal Windows platform a shot at providing that platform for you. So good luck. Remember, I'm here to help, and reach out with any questions.